So in the previous two videos we went through a lot of background information, but we haven't really done a lot of actual example work. So I'm going to go through one sort of extended example here about position, velocity, and acceleration, and hopefully that'll give you the experience that you need to make it through the problems tomorrow. So here's this example. An object moves along the x-axis with position at time t greater than or equal to 0, given by p of t equals 4 minus t squared, quantity squared. I should point out here, sometimes this function will be called, instead of p of t for position, sometimes they'll call it x of t or y of t, depending on whether it's moving along the x-axis or the y-axis. So just heads up, it's not uncommon to see a function called x of t. So we've got four parts here, and we'll go through them one at a time. So part A, find functions for the velocity and acceleration of the object. So I'm hoping very much that you guys will know how to do part A. That if we have a position function, how am I going to find velocity and acceleration functions? Well, we should do that by taking the derivative of position to get velocity, then the derivative of velocity to get acceleration. That should be a pretty basic derivative for us to do based on the lessons we had yesterday, so I want you to pause the video and make sure that you can do both of those. So find velocity, find acceleration, and then we'll check in and talk about it. So for velocity I'm going to take the derivative of position. Right? Now hopefully you guys recognize that this is a chain rule problem. There is a squared function, and within that squared function I have 4 minus t squared composed. Right? So to do the derivative of that, I'm going to do the derivative of the x squared function. That gives me 2 times the inside composed function, and remember we leave that alone, 4 minus t squared, and we multiply by the derivative of that function that was composed inside, negative 2t. The power up here, I suppose, is a 1. We brought the 2 down and subtracted 1 from that. So that's my velocity function. Now, I would argue we might as well make that a little bit prettier. We can say v of t is negative 4t times 4 minus t squared. Right? And to me, that looks like a good velocity function. We know we like to have things factored, so that feels good to me. But I need to go on and find my acceleration function next. And you sort of have a choice here. You could do the product rule on this, or we could realize, I could just distribute that negative 4t and then do the derivative. Right? So I'm still working with v of t. I'm going to write it as negative 16t plus 4t cubed. So that again is still my velocity function. Now when I go to find the acceleration function, the derivative of that, I'll get negative 16 plus 12t squared. And there's my acceleration function. Alright, so next up is part B. Part B asks us to determine any times at which the object was at rest. So if you don't remember offhand, pause the video or look back at your notes. How do we determine when an object or when a particle is at rest? We know that an object is at rest. It's at rest when the velocity is 0. Right, so if I'm going to find out when this object is at rest, I'm going to need to set my velocity function equal to 0. Now you'll notice that as I'm doing these things, I'm actually listing, like I'm writing each of these things as v of t, and then when it changes to acceleration, I write that. And the reason that's kind of valuable is that when I need to set the velocity equal to 0, I can set any of these versions of velocity equal to 0. In my opinion, the best one to use is this middle one that I have boxed, because it's already factored. Right? When I set that equal to 0, I'll just have 0 equals negative 4t times 4 minus t squared. And the reason that's particularly nice is that because it's factored, I can use the zero product property and just set each of those pieces equal to 0. Right? I'll have negative 4t equal to 0, and then I'll also have 4 minus t squared equal to 0. So if I solve for this one, I'll get t equals 0. For this one over here, I'll have t squared equals 4, which means t is plus or minus 2. But it was mentioned in the problem that we are only looking for time greater than or equal to 0. So the only times that the object is at rest is at time 0 and then at time 2. It would have been at rest at time negative 2, but that's not one of the times that we're considering, and so we don't even list it as a possibility. And so now we can move on to part C of the problem. Part C had asked us to find the position, velocity, and acceleration at time 3. So really all that amounts to is taking your value of 3 and evaluating your position function, your velocity function, and your acceleration function all at that time of 3. Right? So I will do that now. I'm going to sort of make some more room for myself here. So for the position at 3, we can compute p of 3 by doing, this is my position function, 4 minus 3 squared, so that's 9 squared. So p of 3 is negative 5 squared, so the position is 25. So this is all part C that we're doing. The velocity at time 3, so here again you have a choice. Like any one of these 3 velocity functions could be used depending on which you feel is going to be easiest for you. I'm just always a fan of the factored one, so I'm going to go with that one. V of 3 will give me negative, so if you look at this, negative 4 times 3 will give me negative 12 times 4 minus 9. So V of 3 is negative 12 times negative 5, and that means that V of 3 is 60. So I found my position at time 3, found my velocity at time 3. Now I just have to find acceleration, and I'll use my one acceleration function here for that. When I do A of 3, I will have negative 16 plus 12 times 3 squared, which is 9. So my acceleration at time 3 will be negative 16 plus 144. And so that means that A of 3 is 128. So that's my acceleration. Now the final part, part D, had asked us to describe the motion of the object. Which direction is it moving? Was it speeding up or slowing down? And so we'll move sideways one more time to do that one. So first of all, how do we determine whether an object is moving right or left? Right, well, based on the velocity, because the velocity is positive, we say that the particle is moving to the right. Now, when velocity is positive, it could mean up, it could mean right, it could mean, forward, but because this problem said it was moving along the x-axis, that's what tells me that it's moving to the right. The other big question there is the object speeding up or slowing down? And I hope you remember from the previous slides, we tell that an object is speeding up or slowing down by comparing the velocity and acceleration, right? Are these two things working together and causing the object to speed up, or are they working against one another and slowing it down? And because these both have the same sign, because they're both positive, the object is speeding up to the right. So, again, if velocity and acceleration had been different signs, one with a positive and one with a negative, we'd say that the object is slowing down. But as it stands, they have the same sign, so they're speeding up. Tomorrow in class, we'll get a chance to practice lots of these. As I've said in all the others, if you have questions, write them down, be ready to ask them about them. I'll see you then.